Today we're tackling something huge, a crisis that has, really defined our modern industrial age. We're talking about the relentless flood of disposable waste, especially plastic, that just pours through our economy.
It's staggering. I mean, if you need a single statistic to really get your head around the scale of it all, think about this. Every single minute of every single day, the equivalent of a full dump truck load of plastic waste gets dumped directly into our
With
oceans.
dump truck a minute,
Oh,
that's almost impossible to visualize, and it all stems from this linear system, this take, make, dispose economy.
exactly. It's not just inefficient, it's a profound failure of design. It's a systemic flaw, really. We built a system that treats our planet's resources as if they're infinite, and it treats waste as, well, someone else's problem. And the result is this massive global plastic waste crisis that demands a radical intervention, not just cleanup, a complete overhaul.
Okay, so that's our mission for this deep dive. We're going to try to cut through all the noise and really dig into the solutions presented in our source materials. And it looks like it's a two-pronged approach, really. First, we have to make this huge shift toward regeneration and circularity, so ambitious reuse and refill models.
Right. Stopping the problem at the source.
Exactly. And then the second part is dealing with the mess we've already made. So rapidly advancing recycling technologies to handle the monumental amount of waste that's already out there.
You have to do both. You have to turn off the tap and you have to mop the floor.
Mhm.
And to really grasp the scale of this shift, we have to start with the foundation, the philosophy behind it. It's not just about being less bad.
Mm.
The real starting point is a concept called regeneration.
Regeneration, what does that mean in this context?
It means putting life-living systems at the absolute center of every single action and every decision we make. It's a design philosophy that's all about restoring, renewing, and revitalizing systems, both human and natural.
And that ties directly into the other big idea here, which is circularity. We're moving from that straight line you mentioned to a closed loop.
A closed loop, exactly. The Ellen MacArthur Foundation has a great definition for it. They call the circular economy a systemic framework where materials literally never become waste.
Mm.
And in that system, nature is actively regenerated.
So the whole point is to decouple our economic activity, things like growth and profit, from having to consume finite resources.
Yes, it forces you to completely rethink a product's life. It's all about maintenance, extending its use, reusing it, refurbishing it, remanufacturing it, doing all of those things multiple times before you even think about recycling the raw materials. Recycling becomes the last resort, not the first thing you reach for.
I'm looking at this framework from Project Regeneration, the Nexus, and it shows just how interconnected this all is. It's not just about waste. It's everything from afforestation to agrivoltaics, electrify, everything. But I have to stop you because two things on this list jump out at me as, well, they seem totally unrelated to packaging. Beavers and compassion.
Ah, yes. That's the beauty of this holistic approach. It thinks in systems. So why beavers? Why are they on a list with high-tech solutions? Well, because they are nature's own engineers.
Nature's engineers.
Absolutely. When beavers build their dams, they restore entire riparian zones, they raise the water table, they create natural fire breaks, they trap sediment, and they purify water. Their engineering work actually sequesters carbon and boosts biodiversity. There are, in effect, fundamental regenerative agents.
Wow. So protecting and reintroducing beavers is literally a climate solution that regenerates land and water. That makes sense. But what about compassion? How can a feeling be part of a circular economy?
Compassion is the bridge to equity, to social justice. The whole regenerative shift requires us to think in systems, and that has to include how these big economic changes affect people, affect communities. Compassion means designing systems that are fair, systems that don't just dump the burden of waste or pollution onto marginalized communities, which is what the linear economy has done for decades. It's the equity piece.
That reframes the whole thing. We're not just building better bottles, we're changing infrastructure, ecosystems, social structures. The sources lay out 6 big priorities for action: equity, reduce, protect, sequester, influence, and support. So let's start with the most critical one that falls under reduce: designing waste out of the system from the very beginning.
That's where you have to start.
Hmm.
The EPA's own waste management hierarchy mandates it. If you look at that pyramid of strategies, right at the very top, the highest priority is source reduction and reuse. Everything else, recycling, energy recovery, landfills, it's all below that. The best solution is to not generate the waste in the first place.
And you'd think that makes perfect sense, but from a corporate perspective, this has to be more than just, good PR. The business case for refillable and reusable packaging has to be rock solid for companies to make that kind of investment.
Oh, it is. Especially when you look at it over a longer time horizon. Environmentally, the wins are obvious, right? You reduce the need for virgin resources, you cut manufacturing energy, you curb pollution. But for the business itself, the long-term benefits are huge cost savings. You're buying way fewer raw materials. And think about it, if you switch to shipping lightweight concentrates instead of big, bulky bottles of mostly water, your transportation and fuel costs just plummet.
And then there's the brand loyalty aspect.
A huge aspect. You're building loyalty with this rapidly growing group of consumers who are making decisions based on environmental impact.
Right, but the average person is still looking at the immediate price tag. And durability costs money up front, which is why we need to talk about the life cycle assessment, the LCA. This is where the data really proves the value of reuse. And there's one critical metric, the break-even point.
This is maybe the single most important piece of data to have in this conversation. The analysis shows that the total environmental impact of a reusable container becomes less than its single-use equivalent after only, get this, 4 to 13 uses.
Just 4 to 13 times.
That's it. So a reusable coffee cup, a detergent bottle, whatever it is, it only needs to be used a handful of times to completely justify its existence from an environmental standpoint.
I want to dig into that initial hurdle, though. Why does a reusable container, which is obviously better long-term, start out with a higher carbon footprint than a single-use plastic one?
It's all about material science and designing for longevity. A reusable container has to be tough. It's made from durable stuff like thick-walled polypropylene or PET, sometimes even metal or glass, so it can handle being washed and transported and refilled over and over. Manufacturing those durable things is just more energy-intensive at first than making a flimsy single-use bottle. That's your initial GWP, your global warming potential cost.
But once you use that container, say, 5 times.
And you've basically amortized that carbon cost across 5 products. And from that point on, the environmental ledger permanently flips in favor of the reusable system.
And the long-term benefit is huge. The sources say that if you push that cycle to 20 uses or more, those reusable containers can cut their overall global warming potential by up to 80%. That's compared to the continuous emissions from making and throwing away 20 different single-use bottles.
Think of it like this. The single-use model has a small carbon hit per unit, but it just stacks up relentlessly. Every day, a new bottle, a new carbon output. The reusable model takes a bigger hit up front, but then it enters this long period of dramatically lower impact. It's an investment in sustainable infrastructure.
Okay, let's bring this down to a practical level. One of the big challenges with reuse is logistics, especially for things like cleaning products, which can be concentrated or even hazardous. How do you make refilling simple and safe? The NAW system, developed by ALPLA, seems to have an elegant answer.
The NOW system is a masterclass in designing for circularity, specifically around concentrates. You have to remember, traditional cleaning products are like 90% water. So companies are shipping massive, heavy bottles of water all over the world. It's incredibly inefficient. The NOW system flips that on its head.
So walk me through it. How does it work? And what are the material savings?
The material savings are over 80% compared to the standard ready-to-use bottle. It's incredible. The concentrate comes in this tiny, ultralight 80 milliliter bottle made of HDPE plastic. It weighs just 10 grams. The consumer just buys this tiny refill and slots it into the main durable reusable container.
And that main container has a reusable trigger pump. That pump is the key, isn't it? Because those things are a nightmare to recycle. They've got metal springs, different kinds of plastic, rubber bits, all fused together.
Precisely. That is the design genius of this system. It uses a reusable spike that locks the little concentrate bottle in place. And crucially, that main trigger pump, that really hard to recycle component, it stays permanently attached to the durable main bottle. Its life cycle is extended almost indefinitely. You're only ever replacing the tiny, lightweight, single-material concentrate bottle.
So they've isolated the part that has to be recycled, the little refill, and made it as small and simple as possible, while maximizing the life of the hardest part to recycle, the pump.
Exactly. And because that small refill bottle is 100% HDPE, it's fully recyclable. It's also flexible enough that you can make it with up to 100% rHDPE that's recycled high-density polyethylene. So you're closing the loop. It minimizes material, it slashes shipping costs, it's safer for the consumer, and it solves a huge recycling headache.
That focus on systems efficiency really shows why reuse is just exploding commercially. This isn't just some niche trend anymore, is it? It's becoming a core industrial strategy. Let's talk about the market growth for reusable packaging.
The numbers are pretty stark. The global market for reusable packaging was estimated at $135.8 billion just for 2024. And it's projected to grow to $190.1 billion by 2030. That's a compound annual growth rate a CAGR of 5.9%. This isn't marginal growth. This is a fundamental shift in how goods are packaged and moved around the world.
What's driving that almost 6% growth year over year? Is it just consumers demanding better options, or is something else pushing it?
It's a powerful mix of forces, really. On the outside, you have governments getting much stricter about single-use plastics. You're seeing bans, taxes, mandatory recycled content laws. And then internally, corporations are feeling the pressure through their own ambitious ESG goals, environmental, social, and governance goals. If you want to hit net zero, you pretty much have to move away from these material-intensive linear models.
And it's crucial that even with the higher upfront cost for the durable packaging, the long-term operational savings are starting to win the argument.
That's right. The initial CapEx is higher, no doubt. But the recurring operational costs, buying virgin materials, paying for disposal, shipping, they are so much lower over the product's life. Companies are finally realizing that these CSR, corporate social responsibility initiatives, aren't just feel-good marketing. They're strategic investments in their own future resilience.
So if we break down this market, what materials are winning out for durability and which sectors are leading the charge?
Well, plastic is still dominant, holding over 48.7% of the market share this year. But this isn't your standard throwaway plastic. This is highly engineered, durable stuff. HDPE, PPPT, materials chosen because they're lightweight, but also chemically resistant and can handle dozens of trips and washes. And containers, crates, bins, bottles are the biggest product segment by far. A massive 37.1% share just because they're so versatile.
And the food and beverage industry, which gets so much heat for its packaging waste, is still the biggest single driver.
Oh, absolutely. Food and beverage has the largest end-use market share at 38.7%. And that's for a few reasons. One, the public and regulatory pressure on them is immense. Two, the explosive growth of online grocery and food delivery, which needs robust standard packaging. And three, critically, they already have some models for this, right? Like glass bottle deposit systems or keg distribution for breweries. The idea of a return system isn't totally foreign to them.
Okay, so the tech is there, the business case is solid. The biggest hurdle left seems to be, well, us. Consumer inertia. And the logistics of getting all this stuff back, especially in big, messy places. So let's look at how technology is solving this. For example, in institutional food service, using the model from reusables.com.
Reusables.com figured out why earlier reuse systems failed. They put too much friction on the consumer. You had to download an app, pay a fee, deal with some confusing deposit. Their solution is a hardware-enabled SaaS model that just makes the user experience disappear.
It's this tap-to-reuse system. It's meant to be completely frictionless.
Yeah.
How does it actually work for, say, a student in a dining hall or a hospital worker?
They just eliminated all the old barriers.
Yeah.
There are no sign-ups, you don't need a separate app, and this is critical, no deposits required from the person using it. The system usually just integrates with whatever ID card you're already using on campus or at the hospital. You grab your meal, and when you're done, you just go to a return bin and tap your card. That's it. The container is logged back in.
By taking away all those psychological hurdles, the cost, the hassle, the sign-up, they must get incredible compliance rates.
Phenomenal compliance. Their clients are reporting 99% plus return rates.
Right.
I mean, that is the holy grail for circular logistics. And they actually save money in the first year because they just stop buying endless mountains of disposable containers. One university client, for example, avoided over 25 tons of packaging waste and over 100 tons of carbon emissions in just 2 semesters.
Those are the kinds of numbers that get a CFO's attention. And the hardware at the center of this must be those smart return bins.
The smart bins solve the infrastructure problem. They give you 247 automated returns, which is huge. And maybe more importantly, they ensure the returns are contamination-free. They use sensors and smart locks to make sure you're returning the right item, which makes the whole washing and sanitation process much more efficient. That 24/7 access is a game changer. It gets the containers back into the system fast.
Okay, so let's pivot from the containers we see every day to the hidden world of industrial reuse. The pallets, the bins, the crates that move everything behind the scenes. Tracking this stuff, this returnable transport packaging or RTP, it used to be just an annoyance, lost inventory, but now it's mission critical.
Absolutely. I mean, when you have hundreds of thousands of these specialized plastic bins or metal racks, and they can cost hundreds, even thousands of dollars each. Losing them or just letting them sit idle is a massive financial drain. Advanced tracking is now the strategic backbone for managing these valuable assets.
And I'm guessing simple barcodes or those passive RFID tags just don't cut it anymore when these things are moving all over the country, in and out of trucks and warehouses. What does modern tracking look like?
We've moved into what are called hybrid real-time location systems, or RTLS. They don't rely on just one technology. They combine multiple inputs. You've got ultra-wideband, or UWB, for super accurate indoor location down to a few centimeters. You've got Bluetooth Low Energy, BLE, for cost-effective scanning in big hubs. And then GPS and Wi-Fi for when the assets are outdoors or on the road. This multi-tech approach gives you continuous, really granular visibility. It eliminates all the old blind spots in the supply chain.
So the system knows not just where an asset is, but what it's doing and if it's in the right place at the right time.
Exactly. And that visibility turns into active management. You can set up what they call automation triggers. So the system can send an automatic alert to a plant manager if, say, a batch of reusable totes has been sitting on a loading dock for more than 48 hours. Or if a valuable asset leaves a geofenced area. It stops costly shrinkage and it speeds up turnaround times.
And all that data must feed into bigger optimization strategies, making the whole pool of assets work smarter.
That's the highest value part of it all. Asset pool optimization. The system crunches all this data, historical and real time, and it spots systemic problems. It might see that, 30% of your transport crates are consistently sitting idle in the Northeast for 10 days longer than they should be. So it'll recommend redistributing them to prevent a shortage that's about to happen in the Southwest.
So you're not just stopping losses, you're actively building a more efficient and resilient supply chain.
And the ROI is there. Companies using these hybrid RTLS systems are reporting really dramatic results, up to an 80% reduction in lost assets. And they're speeding up their return cycles, often cutting them by several days. This means they can run the same level of production with a smaller, more dynamic tool of RTPs. It's a truly closed loop.
So the message from the first half of this deep dive is really clear. Reuse and refill are the top priority, economically and environmentally. But, we have to be pragmatic. There's a mountain of plastic waste that already exists, and some products will always have an end of life that requires material recovery. So recycling has to be an essential parallel strategy.
It's absolutely essential, but we have to be honest about its track record. Historically, the global recycling rate has been, frankly, shocking. Of all the plastic ever made between 1950 and 2015, only about 9% of it was actually recycled. The rest, incinerated, or it's still sitting in landfills and our oceans. We have to do dramatically better.
Why is that rate so stubbornly low? Even with all this awareness and new tech, what are the fundamental barriers holding the system back?
Well, the economic barrier is the big one. Virgin plastics, which are made from cheap fossil fuels, are often just cheaper. They typically sell for between $1,000 and $1,500 a ton. Recycled materials, on the other hand, are complicated and expensive to process. They can cost anywhere from $200 to $1,200 a ton, sometimes even more. That price gap just undercuts the market for recycled content. It makes it cheaper for a company to just buy new plastic.
And then there's the technical side. The waste stream itself is just a mess. It's contaminated. It's a mix of a dozen different kinds of plastic. It's got these complex multi-layer packages that you just can't separate easily.
Exactly. So traditional mechanical recycling often creates a lower quality material. It might have inconsistent color, it's weaker, the molecules are damaged, and that means you can't use it in high-value applications, like new food packaging, which further kills the market for it.
Which is why the new wave of mechanical recycling isn't just about bigger grinders. It's about digital integration to fix that sorting problem first. Mechanical recycling is still the fastest and cheapest method, but the output has to be pure to be valuable.
And the synergy between AI and robotics is what's changing the game here. You have AI recognition software from companies like Great Parrot or Zen Robotics that sits over the conveyor belts. It uses sensors and machine learning to identify and categorize all the different polymers at incredible speeds. Then robotic arms, guided by that AI, physically sort the waste streams with just, unparalleled precision.
How much more accurate are we talking here compared to a person or an older optical sorter?
We're talking up to 95% accuracy in identifying and separating out single polymer streams. And that level of precision is absolutely critical because even a small amount of contamination can ruin a whole batch of recycled material. This automation not only makes the recycled plastic more valuable, but it also drives down labor costs by as much as 40%.
Okay, so once you've sorted the plastic, say you have a pure stream of PET from old bottles, it's often weaker than virgin PET. You need a way to restore that quality so it can become a bottle again.
Right, and that restoration process is called solid-state polymerization, or SSP. When you mechanically recycle PET, the long polymer chains get broken down. That's why it loses its strength, what's called its intrinsic viscosity, or IV. SSP is a process where you gently heat the recycled plastic flakes in a vacuum. The heat encourages those broken polymer chains to link back up, to repolymerize, but without fully melting the plastic.
And that's essential for it to be used in food contact products again.
It is. SSP allows recyclers to get up to 95% recovery of the original IV. So you're effectively restoring the strength and safety you need for brand new food-grade bottles. And it's also more energy efficient. It saves about 40% of the energy compared to the old high-heat melt processing methods.
Okay, so now let's talk about the plastics that mechanical recycling just can't touch, the really contaminated stuff, the mixed bundles, the complex multi-layer films. This is where we get into chemical recycling.
Chemical recycling is the necessary next step for those really challenging feedstocks because it doesn't just sort plastic. It breaks the polymers all the way down to their fundamental molecular building blocks.
Monomers, oligomers, or something called syngas.
The huge advantage is that the output, which is often called pyrolysis oil, is chemically indistinguishable from virgin feedstock. You can use it to make brand new virgin quality plastic for any application.
But chemical recycling is also really controversial, isn't it? A lot of critics say it's just a very expensive way to burn plastic, that it's super energy intensive and doesn't actually recover much material.
And that skepticism is valid and important. It's what drives the need for more efficient and transparent technologies. Some of the older processes are very energy intensive. The key is to focus on the technologies that are genuinely breaking the material down for reuse, not just for fuel. We have three main methods here: depolymerization, pyrolysis, and gasification.
Let's start with depolymerization.
Depolymerization is the most precise method. It uses chemical catalysts to literally reverse the polymerization process. It takes plastics like PET or nylon and turns them right back into their original monomer building blocks. Since those monomers are identical to virgin ones, you can just repolymerize them into new, high-quality plastic.
And then there's pyrolysis, which seems to be the most common form.
Right. Pyrolysis takes mixed plastic waste and heats it to extremely high temperatures. We're talking 300 and 900 degrees Celsius, but in an oxygen-free environment so it doesn't burn. Instead, the polymer chains crack and break down into a valuable liquid, a kind of synthetic crude oil, and some gases. That oil can then be refined back into naphtha, which is the base for new plastics. The big challenge is getting a high yield of quality oil, not just low-value gas or char.
And finally, gasification for the absolute messiest waste streams.
Gasification uses even higher temperatures, up to 1500 degrees Celsius, with a little bit of oxygen or steam. This process can break down almost any carbon-based material, even unsorted municipal solid waste, into something called syngas. Syngas is a mix of hydrogen and carbon monoxide. It can be used as a fuel, but more importantly, it can be converted into chemical feedstocks like methanol to produce new plastics. It's the most robust process for the most complex waste.
Given those incredible temperatures, especially for pyrolysis, how are researchers making this whole process greener and more efficient?
The key is advances in catalysts. They speed up the reactions and, crucially, allow them to happen at lower temperatures, which saves a ton of energy. And we're seeing big breakthroughs with greener, non-metallic catalysts. For instance, organocatalysts, which are carbon-based compounds, can facilitate depolymerization at much milder temperatures, and they avoid the toxicity you sometimes get with heavy metal catalysts.
And the most cutting-edge stuff in this area seems to be these ionic liquids.
Ionic liquids, or ILs, are often called green solvents. They're basically salts that are liquid at room temperature. You can tune their properties, and they can act as both a solvent and a catalyst at the same time. In some processes, using ILs has been shown to reduce the energy demand by up to 30% compared to traditional catalysts. That's a huge improvement in the economic and environmental viability of chemical recycling.
Which brings us to what feels like the most sustainable process of all, one that actually mimics nature: biological recycling.
Right, this is where we harness nature's own tools, specialized microorganisms and the enzymes they produce. These enzymes work in very mild conditions, often just room temperature or a little warmer, so they require way less energy than the other methods. The big drawback historically was just speed. These processes used to take weeks or months, which just wasn't scalable for industry.
But bioengineering is changing that speed problem, right?
Absolutely. We're seeing huge breakthroughs in synthetic biology. For example, there's an engineered enzyme called fast PTase. It's up to 6 times faster than the version found in nature. It can break down a post-consumer PET bottle in about a week. That's fast enough to be commercially interesting.
And there's a company, Carbios, that's already proving this can work at industrial scale.
Carbios is the pioneer here for sure. They use an optimized enzyme that can depolymerize 97% of semi-crystalline PET in just 10 hours at a gentle 65 degrees Celsius. The enzyme is super specific, so it creates really high purity monomers that can be used again, and they are now scaling this up into large industrial plants. They're proving that biological recycling can handle massive amounts of waste.
We should probably pause here, though, because there's a big point of confusion for consumers. When we say biological breakdown, people often mix up recycling with biodegradability.
That is such a critical point. A lot of so-called bioplastics, like PLA, are marketed as biodegradable. But that often means they require very specific conditions, namely an industrial composting facility that operates at high heat between 58 and 62 degrees Celsius with just the right humidity and microbes. If you throw a PLA cup in your backyard compost or it ends up in the ocean, it's not going to break down quickly. It can still persist for a very long time. It shows the need for clear labeling and, again, the right infrastructure.
So finally, let's look at the most radical idea of all. Innovating materials, so we move beyond just managing waste and instead create materials that are regenerative from the very start. Sway's seaweed solution seems like the perfect example of this.
Sway is doing something truly different. They're offering a genuine, home-compostable replacement for single-use plastics. And they're targeting some of the worst offenders. LDPE plastics, like retail bags, shipping mailers, flexible pouches, the stuff that's durable enough to pollute for centuries, but we only use for a few minutes.
So what makes the Sway material different from other bioplastics that have tried and failed to catch on?
I'd say there are three huge differentiators. First, the product is carbon negative, just because of its feedstock. Second, it's high performance and designed to be cost competitive with regular plastic. And third, and this is the most important part for the planet, their patented seaweed resin is proven to completely biodegrade in the ocean or in soil within 30 days. And it leaves no microplastics behind.
That 30-day biodegradability in a natural environment is a complete game changer. But the biggest barrier is always getting industry to adopt something new. Does this require building entirely new factories?
And that is the most brilliant part of their strategy. They call it drop-in scalability. Sway knew that asking the global plastics industry to retool its entire infrastructure would take decades and billions of dollars. So they engineered their seaweed resin to work seamlessly within the traditional plastic manufacturing infrastructure. The same machines that make LDPE films can use their resin. This means existing manufacturers can adopt it almost overnight without massive new capital investment.
And the feedstock itself, the seaweed, it closes the regenerative loop. It offers benefits way beyond just the packaging.
Seaweed cultivation is what you could call a marine ecosystem architect. It actively sucks CO2 out of the water, so it's a huge carbon sink. It helps fight ocean acidification, which is great for shellfish and coral reefs. It creates habitat, which increases biodiversity. So by creating a big market for this regenerative crop, Sway is supporting coastal jobs and directly healing the ocean. It's the full circle of biological and economic regeneration.
So we've detailed all these incredible technological solutions, but at the end of the day, all of them, from smart bins to seaweed films, have to work in the real world. And that means we have to confront consumer resistance.
Right. Why are people so reluctant to embrace these circular models, even when the environmental case is so clear and the long-term economics are often better?
It's a great question.
It's really rooted in what behavioral economists call the status quo bias. We are creatures of habit. We're so used to products being cheap, disposable, and immediately convenient. The idea of having to return something or concerns about hygiene with shared items, it creates this friction that stops people.
So we can't just tell people to change. We have to design the systems to make the circular choice the easiest choice.
Precisely. The sources point to three key strategies for this. First is convenience. The circular option have to be as easy or even easier than the linear one. That means investing in things like those automated smart return bins, designing super intuitive sharing platforms, and making sure the systems are everywhere.
Second, you need strong incentives. If you want people to change their behavior quickly, money talks.
Economic tools are incredibly powerful. Things like subsidies for circular products, tax breaks, and maybe most effectively deposit refund systems, or DRS. The success stories are just undeniable. Look at Norway. They pioneered a DRS for beverage containers, and they now have an astonishing 95% PET bottle recycling rate. You put a small financial value on the package, and you create an almost perfect guarantee it will come back.
And finally, people have to actually believe in the system. They need trust and education.
Transparency is everything. Companies have to be crystal clear about the environmental benefits and what happens to the products. You need education campaigns to get rid of those old misconceptions about hygiene or inconvenience and to shift the social norm. It needs to move from, this is an extra chore I have to do, to this is just how we do things now.
And beyond just nudging individuals, you need policy and regulation to change the entire system, to make sure circular solutions can even compete with cheap, subsidized virgin material.
Policy is critical for pricing in the true cost of waste. We're seeing a rapid global move toward extended producer responsibility, or EPR schemes. Under EPR, the company that makes the product is financially and operationally responsible for its entire life, from design to collection and recycling. It forces them to design for durability and recyclability from the start. We're also seeing more eco-design regulations that set minimum standards for how long a product must last or how easy it is to repair.
And the big one on the horizon, the thing that could unify all of this globally, is the negotiation of a legally binding global plastics treaty.
The treaty, which they're aiming to finalize by 2025, could be the most significant environmental policy in decades. It's all about creating a shared global commitment. The key goals are to phase out the most unnecessary and problematic single-use plastics and to set legally binding targets to dramatically increase the use of recycled materials everywhere. It creates the economic certainty that companies need to invest in circular infrastructure.
Let's tie this all back to where we started, with that holistic view of regeneration. We can look at that Nexus rating system, which judges solutions on 5 criteria: carbon, biodiversity, women, culture, and social justice. What do those scores tell us about how circularity performs beyond just the environmental math?
Well, on the hard science metrics, circularity scores exceptionally well. It gets a really impressive 8.33 for carbon and a strong 6.80 for biodiversity. And that makes perfect sense, right? If you stop extracting virgin materials, you stop destroying habitats. If you stop polluting landfills and oceans, you protect ecosystems. Moving to a circular model is one of the most powerful levers we have to fight climate change. It could cut global emissions by nearly 40%.
But the score for social justice is noticeably lower. It's at 5.75. It's still a positive score, but why is there that big of a gap compared to carbon and biodiversity? What are the social challenges here?
That score points to a really critical issue: environmental and resource justice. Historically, the linear economy has pushed its negative impacts onto the most vulnerable people. You see this with incinerators and waste facilities, which are disproportionately located in low-income or marginalized communities. And for decades, wealthy countries have just exported huge amounts of their contaminated plastic waste to developing nations, completely overwhelming their local infrastructure and turning them into de facto dump sites.
So a truly just circular economy has to stop that practice of just shipping our trash somewhere else. And it has to ensure that the new circular infrastructure we build at home actually benefits all communities.
Exactly. To get a higher social justice score, you have to be intentional. It means making sure local communities have ownership and control over new recycling facilities. It means ensuring fair labor practices in the new reuse supply chains. And it means demanding total transparency about where all this material is going. The concept of circularity is regenerative, but its implementation has to be equitable to fix the deep injustices of the past.
And that really leads to the final hurdle, doesn't it? The cultural one.
We're fighting against a century-long habit of disposability. Even if a refill system is cheaper in the long run, even if the tech is totally seamless, like we saw with that 99% return rate, there is still this massive challenge in convincing the global consumer to stop reaching for the single-use option out of pure habit. The success of all this technology depends on making that social norm shift and making it happen fast.
So today's deep dive has really underscored one central truth. Solving this plastic crisis requires a very deliberate dual strategy. First, we have to follow that reduce mandate by prioritizing reuse and refill systems, which we've seen can hit their environmental break-even point in just 4 to 13 uses. And they're supported by these elegant material-saving logistics like the NOW concentrate system.
And at the exact same time, we have to aggressively fund and scale up the technology. That means perfecting mechanical recycling with hyper-accurate AI sorting. It means making chemical recycling truly viable with advanced catalysts like ionic liquids and accelerating the huge potential of biological solutions like enzymes. And beyond all that, it means supporting the creation of truly regenerative materials like those carbon-negative seaweed plastics that are designed to just return to nature.
The global targets are incredibly ambitious, a 50% recycling or composting rate by 2025, and pushing for 95% recovery of collectible plastics by 2030. And these targets demand so much more than just asking consumers to try harder. They demand a complete re-architecture of how we make and move things.
Which brings us back to our final thought for you, the listener. We've established that the material science, the logistics tech, and the long-term economics for circularity are, for the most part, proven. These systems can already match or even beat single-use options on cost and performance. So if the hardest technical and economic problems are being solved, then the greatest remaining hurdle might be purely cultural. How quickly can we convince ourselves as a global society to choose the slightly more responsible and maybe more rewarding ritual of reuse over the deeply ingrained seductive convenience of take, make, dispose? That collective psychological shift, that's the final frontier of circularity.